Hello students, this is the recording that goes over every question in the 10B final exam. So let's go ahead and take a look at this. So what we are going to do is we're going to go through each question. So question 1 says match the measurements with their correct quantities and examples. So you can see some measurements over here, and we want to match them up with their correct quantities as well as examples that we see. So we've got 1 meter, 1 kilogram, 0 degrees Celsius, 1 second, 1 milliliter, and you can see all of your options over here. So let's go ahead and talk about these. So remember that 4 of those that we're looking at are what are called fundamental quantities, meaning the most basic measurements that we cannot express using other quantities. So this is distance, which is measured in meters, mass, which is measured in grams, time, which is measured in seconds, and temperature, which is measured in degrees Celsius. Now, that being said, again, distance is measured in meters. You could also say 1 meter is about 1 yard long or 3 feet long. And remember that these quantities are a little bit easier to convert than the ones that we use in America, for example, because they convert with tens by multiplying by 10. Time is still measured in seconds in science, so this is still a fundamental quantity measured in seconds, and 1 second is about the length that it takes for 1 heartbeat to occur. We also talked about mass. Mass is the amount of stuff or matter that an object is made up of. It's similar to weight, but it is not the same thing. So remember, an example of mass would be 1 gram, and that would be about the mass of a single paperclip. Temperature is measured in degrees Celsius in science. Again, this is different than what we usually measure it in America with, in the US with, but temperature in science is measured in degrees Celsius. The reason for this is because it's really simple. It's based on water. 0 degrees Celsius is the freezing point of water, and 100 degrees Celsius is the boiling point of water, which again makes a lot more sense than what we currently use in the US, which is Fahrenheit, and Fahrenheit does not line up as nicely with the freezing and boiling points of water. All right, so the last type of unit we want to talk about was a little bit different. This is volume. So volume is what is called a derived unit because it's actually a combination of fundamental units put together, right? So it can be expressed with other fundamental units. So for example, we measure volume by using cubic centimeters because we can multiply 1 centimeter by 1 centimeter by 1 centimeter to make a cubic centimeter, also what is called a milliliter. So remember, we can actually call it a cubic centimeter or a milliliter. So 1 milliliter is the same as 1 centimeter times 1 centimeter times 1 centimeter. And again, because we're combining different types of units together, that is why volume is considered a derived unit. So at this point, you should be able to understand all of these. We talked about when water freezes. We talked about the units for distance, mass, time, volume, and temperature. We also talked about what approximately 1 heartbeat is related to and what 1 centimeter times 1 centimeter times 1 centimeter is related to. So make sure you pause the video. Yours will be in a different order most likely, so make sure you read carefully and then continue playing when you are ready to continue. The next question is talking about graphing. So we can see here a couple things in our graph, right? We know that this graph is about the amount of sunlight that a plant is getting in hours and the height of the plant that it ends up becoming. So we have a couple statements here, and we'll go ahead and take a look at those in a few moments. But first, let's talk about graphs. So remember, graphs are showing the different variables within an experiment. So the independent variable, remember, is what we intentionally change at the start of the experiment. The dependent variable, on the other hand, is what we measure at the end of the experiment. So for example, when you're taking a look at this situation, the hours of sunlight versus the final height of the plant, the hours of sunlight is what the scientist can control, and therefore this is our independent variable. So the hours of sunlight would be the independent variable, whereas the final height of the plant is what we're measuring at the end, right? So this gets measured at the end, and so the height of the plants would be our dependent variables. Sorry, I know that's very messy. So that being said, once we know the independent variable and dependent variable, we can actually graph them on a graph. And the purpose of a graph is to show the relationship between independent and dependent variables. Now, the independent variable always gets plotted on the x-axis. So this is our independent variable, which is the horizontal axis. And the dependent variable always gets plotted on the y-axis, which is our vertical up-down axis. So again, the hours of sunlight, that's what we could change on purpose. So that was our independent variable. So we put that on the x-axis. So when we talk about sunlight in hours, This is on our x-axis because it is our independent variable, whereas the height of our plant was our dependent variable and should therefore be on the y-axis. So when we talk about the height of the plant, that is going to be our dependent variable on the y-axis. Okay, now the whole purpose of graphing, again, is to show relationships between variables. And the best way to show these is to draw a trend line. So you can see a trend line right here. And the purpose of a trend line, it could be a straight line or a curve that follows the data points as closely as possible. The purpose of this is so that we can make predictions about data points that we have not yet gathered. So for example, you can see here a predicted point. Again, the scientists didn't actually gather real data here, but they can make an educated guess about what would happen based on their trend line. So trend lines allow them to make predictions. Okay, so let's go ahead and take a look at these statements here. Again, in this case, you're actually looking for the statements that are false. So you want the one statement that is false. So taking a look here, again, talking about some information here. Remember, this is our x-axis, and x-axis is where the independent variable goes. Remember, independent variable is the cause or the start of an experiment. On the y-axis, that's where our dependent variable goes, and remember that is what gets measured, right? So this is what we measure at the end of an experiment. It's the effect, okay? And then taking a look here, again, remember the purpose of a trend line is to make predictions. And one of the things that we can see here is that we can predict that the more sunlight you get, right? So as we get more sunlight to the right, we can see that the height of the plant is actually increasing. So additional hours of sunlight means an increase in the height of the plant. So take a look at these statements and figure out which one is false. All right, the correct answer is the one that is actually false. So an analysis of the data shows that as hours of sunlight increase to the right, the height of the plant decreases. Let's see if that is true or false. The dependent variable is the height of the plant in centimeters. Again, we talked about the y-axis being the dependent variable. The independent variable, which is what is intentionally changed in an experiment, is placed on the horizontal x-axis. We talked about what an independent variable is and where it gets plotted. And then we also talked about the purpose of trend lines, right? So this statement says trend line shows a relationship between variables and can be used to make predictions about data. Figure out if that is true or false. Again, you're looking for the false statement, the one that is wrong. All right, so question number 3 is taking a look at velocity. So a car is driving at a pace of 300 meters in 20 seconds. So we want to know what is the car's velocity. So let's take a look at this equation right here. Remember that in order to calculate velocity, we need to know the distance that gets traveled and divide it by the amount of time it took to travel. So distance, remember, we measure in meters, time we measure in seconds, and velocity we measure in meters per second. So that should help us annotate and understand our problem here. So remember, we just talked about how when we talk about meters, we know meters is a measurement for distance. It's a unit for distance. And seconds is a unit for time. And remember, velocity, our answer should end up having a unit of meters per second. So if we know the distance and we know the time, you should be able to plug those in and then make sure you divide them correctly. So the distance divided by the time should give you your correct answer here. Again, these will be in a random order, so make sure that you read carefully and choose carefully. Question number 4 is now taking that same car from question number 3 and saying that it takes about 3 seconds to accelerate to a velocity of 21 meters per second, and therefore we want to know what is the car's velocity, and then, acceleration. And then lastly, is this acceleration positive, negative, or 0? So let's talk a little bit about acceleration. So remember that in order to calculate acceleration, we're going to need the initial velocity, and don't forget the initial velocity, we actually already calculated that in question number 3. We'll need to know the final velocity, which is given to you in this question, question 4, and the amount of time, which again is given to you in this question in question 4. Okay, that'll be plugged in where final velocity minus initial velocity is calculated first, and then from there we can divide it by time, and that will give us our final answer right here. Okay, remember velocity is measured in meters per second, time is in seconds, and acceleration is actually measured in meters per second squared. Remember, the squared part is actually just a part of the unit. You don't actually need to square any numbers. It's all one single unit. So this square doesn't mean you need to do anything. It's just the units for acceleration. Okay. So that being said, depending on the type of acceleration that you calculate, you should know that positive acceleration means velocity is increasing. So if you're getting faster, like you started at rest and then began moving, or in general, you're just getting faster, that is going to be a positive acceleration. Negative acceleration means velocity is decreasing. So if you're either getting slower or if you come to a stop, that is negative acceleration. And then zero acceleration means your velocity stays the same. So either you're at rest and you stay at rest in this example, or you are in motion and you stay in motion with the same speed and direction. Okay, so let's go ahead and take a look again at this question. So we're using the same car from question number 3, and we need to get some information about it. So remember, we can see here that seconds is going to tell me my time, right? So I know by annotating this, this is my time. I'm trying to figure out acceleration, right? That's what we're solving for. And we know that it's accelerating to a velocity of 21 meters per second. Now, what's important here is we know meters per second is a velocity, but we need to figure out if it's our final or initial velocity. So keep in mind that since it's accelerating to 21 meters per second, this is actually the final velocity. Now again, we need to remember the initial velocity was your answer from question number 3. So this is your answer from question number 3. Again, go back up to here, and whatever your answer was here, that's what your V initial is. So this is our V initial. Okay. And again, you already know what your time is. All right, so plugging that in, again, you should be able to plug in your V final here, your V initial from question number 3, and then your time right here. Now, remember that you do need to calculate what's in the parentheses first. So first thing you do is you take your final minus your initial and get that answer, all right? And then you divide it by your time. Sorry, this isn't a 0. This is just a blank, I guess. So let me erase that, and I'll just put a box to show that that's a blank. Oops. Here we go. So take your answer here and divide it by your time, and that will give you your acceleration. So you will notice that you do need to pick more than one answer. So you do need to figure out if it's positive, negative, or 0, and you also need to figure out what the acceleration is. So remember, yours are in random order, but again, you do need to actually pick 2 answers, right? So you need to pick one of the negative, 0, and positive accelerations, and you also need to pick one of the actual answers. Okay, so whatever your actual answer is, pick that one, 7, 6, or 2 meters per second squared. And then again, think about positive. Remember, that means it's getting faster. Negative means that your car is getting slower. And 0 means that your car is staying the same. It's either staying at rest or staying with the same motion. So you should be able to first calculate whether or not it's positive, negative, or 0, but you should also be able to conceptually understand this based on what you know your car is doing here. Okay? So the next thing that we want to talk about is the types of forces and their definitions. So we learned about 7 different types of forces. I'm going to go ahead and go through them right now. So remember, the first 3 forces we talked about were contact forces. So there are 3 types. The first are fluid forces. Fluid forces are the force of any flowing substance. This could be air, this could be water, that physically pushes against an object as the object moves through it. So for example, as you're biking through air, air pushes against you. It's a fluid that pushes against you. Friction forces are the forces that resist an object's motion when it's on a surface. So for example, as you go up a hill, friction is what allows you to move up the hill because it is resisting the motion of your feet so that you don't just slip down the hill. So again, this happens between surfaces. And then elastic forces are when materials return to their original shape when they get stretched or compressed. And this is something like a rubber band or a spring. We also talked about 4 non-contact forces, the first of which is gravity. Remember, gravity is an attractive force that all objects with mass have, but the more mass you have, the more attractive gravity you have. So remember, that's why the Earth has much more gravity than you and I do. Electromagnetic forces are the forces between moving charges. So that's like things between electrons and protons, or it could also be things like magnetic fields. Again, electro meaning the electric forces and magnetic meaning the magnetic forces, but they all have to do with moving charges. And then the last 2 of the 4 non-contact forces we learned about were intermolecular and strong nuclear. So remember, intermolecular forces, it literally says it in the name, it's between molecules. So it's the force that molecules are attracted to each other. So for example, water has really high surface tension because its hydrogens of one molecule are slightly attracted to the oxygens of another molecule. And the strong nuclear force is the strongest force in our universe that we know of that is currently holding together the nucleus of the atom. Remember, if the nucleus of the atom were to fly apart, there would be lots of explosions, and the nucleus of the atom wants to fly apart because remember, all these positive protons are like charges and likes repel. So all these protons want to repel, but the strong nuclear force is strong enough to keep the nucleus together and prevent that repelling. All right, so at this point, you need to match up these four. So electromagnetic, friction, gravity, and fluid. All of the definitions are over here. Make sure you read through them carefully. Again, yours will probably be in a different order, so make sure you read carefully. Question number 6, we're taking a look at Newton's first law, which is talking about what happens with objects in motion. So let's go ahead and first talk about Newton's first law. So Newton's first law says that an object at rest will remain at rest, and an object in motion will remain in motion with constant speed and direction, constant velocity, unless an outside force acts on it. So again, remember, if there are no outside forces, meaning there's no gravity, no friction, no air resistance, then everything stays the same. If it's at rest, it stays at rest. If it's in motion, it stays in motion. However, if there is an outside force, then things do change. So for example, friction and air resistance are resisting motions, resisting forces, which means that they slow things down, right? So friction and air resistance, for example, slow things down. And then things that like where you are applying a force to an object, those are going to speed things up, right? So if you apply an external force, then you're going to speed things up. So taking a look here, we have some different scenarios. So a hockey puck on ice experiences a small amount of friction. Remember, friction is an outside force. So what does friction do to this object? A rock in outer space is moving at 2 meters per second and does not experience outside forces. So what happens to this rock? And then a soccer ball at rest gets kicked by a soccer player, which is an external force. So think about what happens when there is an external force. So again, your options are it will stay at rest, it will speed up, it will slow down, it will stay in motion. You won't use all of these answers, so make sure you read them carefully and choose carefully. All right, question number 7 is taking a look at Newton's second law, which is the equation force equals mass times acceleration. So there are two parts to this. First, we're going to go ahead and calculate the force of the engine if we have a 180 kilogram motorcycle accelerating at 4 meters per second squared. And then after that, once we know the force of the engine, we're going to go ahead and assume that the engine maintains the same force, which means that the force that we originally calculated is going to actually be the same force down here. So these ones will be the same. We'll go over that in a moment. But we would want to figure out what's the new acceleration going to be if a 20 kilogram bag is added. So we're actually increasing the mass here, which is why our acceleration is going to change. So let's go ahead and take a look at that. And again, if you see down here, you're going to actually end up with multiple answers. So make sure you read those carefully. Okay, so Newton's second law of motion says that force is mass times acceleration. So force and acceleration are directly related, but mass and acceleration are inversely related, right? So when there's more mass, there's actually less acceleration, which is going to be important for part 2 of our question when we add more mass to the motorcycle. Now, when we're annotating, remember that newtons tells us force, kilograms is the units for mass, and again, meters per second squared is the units for acceleration. Remember that the squared is just a label. Don't actually square any numbers. Again, it's not actually squaring any numbers. Okay? So let's go ahead and annotate this. So we've got 180 kilograms. Remember, kilograms tells me mass. In this case, it's the mass of my first part. So M1. And meters per second squared tells me my acceleration. Again, the acceleration of my first part, so this is A1, and we want to figure out what is the force, right? So we're going to plug in M1 right here and plug in A1 right here, multiply those together, and that should give you your original force. Okay, so you can see here that you're going to have to choose one of these 3 forces, okay? Yours will be scrambled up, so make sure you read carefully again. Then part 2, we're going to assume that the motorcycle's engine maintains the same force. So again, this means that F1 and F2 are actually the same number. Okay, so based on what you just calculated, you're going to plug in the same number for F2, but divide it now by the new mass. And so the new mass is going to be whatever 180 kilograms from our motorcycle was, plus this new 20 kilogram bag, plus 20 kilograms. So first figure out what that equals, and that's what you're going to plug in for M2. All right, so for your second mass, you're going to plug in whatever 180 plus 20 kilograms equals, because that's your new mass of your motorcycle. Okay, so again, take the same force divided by this new mass, and you should figure out what your acceleration is. All right, now ideally what we should see, so again, choose one of these 3 accelerations. Ideally, what we should see is that if our mass is getting larger, again, mass and acceleration are inversely related, so our second part 2 acceleration we should hopefully see is smaller. If it's not smaller, then we probably did the equation incorrectly, so make sure you double check your work. Okay? Question number 7 is talking about Newton's third law, which is that for every force there is an equal and opposite force. All right, so that means for every force there's an equal force that's also opposite, that's negative. So in this case we have an astronaut and a rocket, and so the force of the astronaut is the opposite or negative of the force of the rocket, but they are equal in amount. Okay, so in this case we have a 70 kilogram astronaut that launches a 5 kilogram rocket, and they're in outer space, so there's no other forces. And the rocket accelerates at 280 meters per second squared to the right, and so we want to know what's the acceleration of the astronaut. Okay, so let's go ahead and talk a little bit about this. So again, every force has an opposing force. So this one we should be able to figure out pretty easily, at least mentally, right? So we should be able to figure out whether or not the astronaut goes left or right based on just the conceptual part of Newton's third law, which says that the astronaut's going to go the opposite way, right? So for example, you can see here, if an astronaut throws an object up, the astronaut drifts down. So in this case, the astronaut's throwing the rocket to the right, so where is the astronaut going to go? Again, think equal but opposite. So we're going to go in the opposite direction, okay? Now, that being said, remember that the rocket and the astronaut are very different masses. So even though they have equal and opposite forces, the way in which they move is actually going to be really different. Think about, for example, how when you jump off of a boat, even though you and the boat have the same mass, you move a lot further than the boat because even though you have the same forces, you actually move a lot further than the boat because you're much smaller. So you can move further because you're not as heavy. The boat, on the other hand, just can't move as far with the same force because it's too massive. So this is what related to what we talked about with the Earth and the Moon. Again, they actually have equal and opposite forces on each other. The Earth pulls on the Moon just as much as the Moon pulls on the Earth. But the moon goes in this gigantic circle and accelerates a whole bunch because it's really tiny, right? So small masses have really large accelerations and can move really fast. The Earth, on the other hand, it has a really large mass, and so it can't move very fast. It can't accelerate very quickly. And so it has a very small acceleration. And that is why the Earth does not rotate around the moon. It really just wobbles in place. Okay, it wobbles at this small area inside of the Earth. Okay? So let's go ahead and take that and apply that to our astronaut. Again, our astronaut is really big, so we're going to guess that our acceleration is going to end up being pretty small, right? Just like our rocket was really small and has a really big acceleration, right? This rocket accelerates at a huge amount. Okay, so let's go ahead and talk again about this equation. So remember, Newton's third law says for every force, there's an equal and opposite force, right? So the force of the astronaut is the negative force of the rocket, but they are equal to each other. And remember that we learned about the equation for force already, which is F equals ma, mass times acceleration. So you can see here that we actually just plugged in that equation. So force is also the mass of the astronaut times the acceleration. And over here, force of the rocket is also just the mass of the rocket times the acceleration of the rocket. So let's go ahead and annotate these. All right, so 70 kilograms, right? Kilograms tells me a mass. In this case, it's the mass of our astronaut. 5 kilograms is also a mass, but in this case, it's the mass of the rocket. And remember, the mass of the rocket accelerates 200 meters per second squared to the right. All right, so that's going to be a positive acceleration. Keep in mind this is a positive acceleration. And again, this is 280 meters per second to the right for the rocket. So this is the acceleration of the rocket. Okay, so that being said, you know the mass of the astronaut, so you can plug that in here. You know the mass of the rocket, so you can plug that in here. Right here is the mass of the rocket. And you know the acceleration of the rocket, so you can plug that in here. So all we need to do then is we just need to solve this. Okay, so the way in which we solve this is we're first going to solve what's on the right side. So first, what you need to do is you need to figure out what's inside of the parentheses, multiply that together. So multiply the mass of our rocket, 5 kilograms, times the mass acceleration of our rocket, 280 meters per second squared, and then make that number negative. So take whatever this is, right, and then we're going to actually make that number negative. So this is now a negative number. So our answer is going to be negative whatever this is. Okay, so negative whatever that was. Sorry, let me erase that. Just clean it up a little bit. All right, so again, this is going to equal negative whatever you get in this part right here. Again, 5 times 280. Okay, now we still have the mass of the astronaut over here, right? We actually already know the mass of the astronaut. That's actually a number that we already have. Let me go ahead. I'll actually just plug in the number to make it look more obvious. Okay, so we know the mass of the, the mass of the astronaut is 70 kilograms, all right, times the acceleration of the astronaut. That's what we're trying to figure out. We're trying to figure out the acceleration of the astronaut. Now, in order to get acceleration of the astronaut by itself, we need to do the opposite of what's next to it. So currently what's next to it it's being multiplied by 70. So instead what we're going to do is we're going to divide by 70. And that'll actually get rid of this. But whatever we do to one side, we actually also need to do to the other side. So on the other side, I'm also going to divide by 70. And that's going to give me my final answer. So the acceleration of the astronaut equals negative whatever this answer is divided by 70. Now this means that we're actually ending up with a negative answer. And if our answer is negative, think about what that means for the astronaut's motion. Again, the rocket was moving in the positive direction. So which way should the astronaut be moving if they're moving in the negative direction? All right, so take a look here. You should be able to figure out this number. Is it to the left, to the right, and what is that number? Again, read that carefully and make sure you choose the correct answer. Okay, question number 9, we're talking about the weight of an object as well as how quickly objects accelerate. So it says you're on Saturn where the acceleration due to gravity is approximately 11 meters per second squared. And we want to know what's the velocity of a 2.5 kilogram bowling ball 3 seconds after it gets dropped, assuming it's in free fall and it's not hitting the ground. And then what will the weight of the bowling ball be on Saturn? Okay, so these are actually 2 different parts. So we're going to go ahead, focus on the first part, and then we'll come back to the second part. So the first part is that gravity, like all forces, causes acceleration. Okay, so gravity makes things faster and faster. So without acceleration, objects would not speed up when you dropped them. So acceleration is really what's causing this object to speed up as it goes down the earth. Now you can see here that what meters per second, what acceleration actually means is that whatever this number is, every second that goes by, the velocity gets that much faster. So after 1 second, the velocity is increased by 9.8. After 2 seconds, it's increased by another 9.8. After 3 seconds, it's increased by another 9.8. 4, another, 5, another, until it's going super, super fast down here. Okay? So this should actually help us figure out how fast this bowling ball is going. So again, if we start out at 0 meters per second, if we start out at 0 seconds and the ball is not moving, that's 0 meters per second. Then after 1 second, we're going to add 11 meters per second, right? Because that's our acceleration here. So we're going to add 11 meters per second. All right. After 2 seconds, you need to add another 11 meters per second, which would be 22 meters per second. And then you should be able to figure out after 3 seconds, how fast is this ball moving? All right, so that should help you figure out the velocity. So you can see here you have 3 different velocities to choose from. And then let's go ahead and talk about the weight. Okay, so the weight of the object is going to actually just be the force due to gravity. So weight is literally just another word for force due to gravity, and the way that we find forces is multiplying mass times acceleration. So force due to gravity, or weight, is also mass times the acceleration due to gravity. So again, these things right here are the same exact thing, which is why their equations are the same. So weight, or force due to gravity, remember we measure that in newtons, mass is measured in kilograms, and acceleration due to gravity is measured in meters per second squared. Again, the squared is not a real number, it's just a part of the unit. Don't actually square anything. So let's go ahead and take a look at this. So we've already talked about velocity, so now we're just going to focus on the weight part. All right, so again, weight is the same thing as force due to gravity, or we could say it's the same thing as mass times acceleration due to gravity. So let's take a look up here. Remember that we talked about 11 meters per second here. This is our acceleration, right? 11 meters per second is our acceleration due to gravity on Saturn. The 3 seconds is time, so we don't actually need time to figure out the weight of it, but we do need to know the mass. And so kilograms right here, 2.5 kilograms is the mass of our object. So we'll plug those in, right? We know mass, we know acceleration, multiply those together, and that should give us our weight. So choose the correct weight. Again, you should have already chosen one of these correct velocities as well. You should have 2 answers. Question number 10 is taking a look at net force. So we have a cart that starts at rest, and then it gets pulled to the left with 30 newtons and to the right with 15 newtons. And we want to know what is the net force, and therefore in which direction does the cart begin to accelerate. So this brings us back to this idea of net force. When forces are unbalanced on an object starting at rest, the net force is going to cause the object to accelerate in the same direction. So you can see here, right, if we have 2 forces moving to the right, they combine to make an even bigger force moving to the right, and so the object moves to the right. It accelerates to the right. Here you can see that we have forces moving against each other, and so since they're working against each other, we actually end up with an overall smaller net force, but it's still going to the right in this case, and so the object still accelerates to the right. If forces balance or cancel out, right, if there's the same amount on the left and the right, then there would be 0 newtons and the object would just stay at rest because there is no net force and therefore no acceleration. So let's take a look here. Again, whatever numbers are on the left side, we actually mark these as negative because left is the negative direction. So this is actually going to be -2, this is going to be -8, and the ones on the right are positive. So positive, 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 positive. Okay, so let's take a look at this. If we have -2 on the left and +8 on the right, what -2 and +8 equal is 6 newtons. And this would actually be +6 newtons, so this one would actually accelerate to the right. Okay, here we've got 10 newtons to the right, 2 newtons to the left, so that's going to be +10 plus +2. And so this actually ends up being a big force to the right, +12. And since it's going to the right, again, the object will actually accelerate and begin moving to the right. Down here, we've got -8 on the left and +8 on the right. So that actually cancels out to 0. And so this object actually will not accelerate. So it will not accelerate. Okay, so let's go ahead and take a look over here at this diagram again. So we've got a cart. Okay, and we have one force moving to the left at 30 newtons. So you need to figure out, is this positive or negative? And then we have a smaller force to the right with 15 newtons. Okay, so 15 newtons. So remember, when we're talking about this, right, here's my graph right here. Remember, the left direction should be negative and the right direction should be positive. So take those numbers, right, whichever one's negative, whichever one's positive, put them together, and that should give you your net force. Okay, if your net force is negative, then the object's going to accelerate to the left, right? So to the left, if your answer is negative. It's going to accelerate to the right if your answer is positive. And it won't accelerate, no acceleration, if your answer is 0. Okay, so that should help you figure that out. Again, you need to choose one of the net forces. Right, so there are 4 of them to choose from, and you need to choose one of the accelerations. So it accelerates to the right, accelerates to the left, or does not accelerate. Question number 11 is talking about pressure now. So a student sits on a balloon in order to pop it. Check off which of the following occurs in this scenario. So basically what's happening here is when we have a student trying to sit on a balloon, what they're trying to do is they're trying to make the balloon smaller. So let's take a look at what happens when we try to make something smaller. So remember that volume and pressure are inversely related, which means that when we have a big volume, we actually end up with a very small pressure, and when we have a small volume, we actually end up with a big pressure. And let's take a look at why that is. So take a look here, we have a big volume. All right, so we've got a big volume, which means lots of space. And so if we have lots of space, then all the particles in here have lots of room to move around. So let's say we've got 1, 2, 3, 4, 5, 6. All right, so we've got particles that have lots of room to move around. And so there's very few collisions, right? So if we have big volume, we actually end up with very few collisions. And if we end up with very few collisions, that means that we end up with very low pressure, because remember, collisions are pressure. So less collisions means less pressure. On the other hand, if I take these same 6 particles and I squish them together, like when I'm trying to pop a balloon, then all of a sudden these 6 particles have a lot less room, right? So when we have a small volume and a small amount of space, then what happens is this small amount of volume actually increases our collisions because they have a lot less room to run around, to move around. And as they're colliding more and more, that's actually going to increase our pressure, which should make sense then of why this pops our balloon, right? So this is why we end up with an explosion, boom. All right, perfect. So again, talking about the balloon is this scenario on the right where we have a small volume and you need to figure out what is happening. So first you need to figure out, you need to talk about pressure, right? So there are 3 different options for pressure. So here are the 3 different options for pressure. So choose what's happening to pressure. You need to figure out what's happening to the volume. Again, this one's pretty easy. I talked about how we're trying to make the volume of the balloon smaller. So choose one of those 3. And then you also need to talk about particle collisions. Let me get a different color really quick. So particle collisions, right? What's happening to those collisions? Choose one of those as well. So you should end up with 3 things that are highlighted, 3 things that are checked off. Question number 11 is talking about pendulums, and pendulums are actually very related to our roller coaster idea when we're talking about potential and kinetic energy. Now remember, when we talk about potential energy, this means that an object is higher up. Okay, so it has increased height as high as it can go. Okay, when we're talking about kinetic energy, on the other hand, we mean that the object is moving faster because it's dropping. So in this case, the height is actually decreasing. Height is decreasing, and so it's actually moving faster. So it's now much faster. Okay, so let's take a look at this. This is actually asking about point C right here, so let's go ahead and talk about these. So a pendulum swings back and forth between potential energy and kinetic energy. So take a look at A, sorry, this should say point A. So point A, we have the highest height. Okay, so we have the highest height. And so at this point, this is actually 100% potential energy. So 100% potential energy. However, it's not moving, so there's no motion. And if there's no motion, no speed, then in this case at point A, it actually has 0% kinetic energy. So it has 100% potential, but 0% kinetic. Okay, and this is actually true as well with point E. Points B and points D actually have 50-50, right? So they have 50 potential because they're at a medium height and 50% kinetic because they're at a medium speed. At the bottom, right here at point C, we're now at the lowest point. So this is the lowest point, the lowest height. And so at this point, we now have 0% potential energy. 0% potential energy. But we are actually moving at our fastest speed. So this is the point at which we move the fastest. And so now we actually have 100% kinetic energy. 100% kinetic energy. All right, so if you take a look over here, at our questions here. So again, we're talking about point C. So we want to see, right, what's happening to its speed, what's happening to its height, and therefore what's happening to its kinetic and potential energy. Please note that some of these are just totally false statements in general. So for example, it has 100% kinetic energy because it's moving at its slowest speed. This would actually never be a true statement because remember, kinetic energy is related to fast speeds. So kinetic energy means you have to have fast speeds. Okay, so keep in mind, think about both the percentage of potential and kinetic energy as well as the actual speeds and heights, because some of these are just totally false statements. You do need to choose two of these, right? So you need to choose one of the potentials and one of the kinetics. Question number 13 is talking about conduction, convection, and radiation. So we have a pot of soup being boiled on the stove, so we need to match up the examples in the scenario to each of these three ways that heat moves, as well as the actual definitions of these three terms. So first off, let's go ahead and talk about conduction. So remember, conduction means that objects actually need to be touching so that their particles can actually collide together. Okay, so for example, when a spoon gets really, really hot, the reason that you can feel it when you touch it is because you're actually in contact touching that spoon, and so particles are colliding with your hand, and that's why it feels hot. Convection, on the other hand, like a convection oven, which has a fan, has to do with fluids moving around. So, for example, hot air rises, cold air falls, or in a pot of water, hot water rises, cool air falls, and cool water falls. And as this happens, as hot liquids rise, hot fluids rise, cool fluids sink, this creates what are called convection currents, which helps to mix up the fluid. So, whatever in our scenario is the fluid, that is actually what's experiencing convection currents, convection heat motion. And then radiation, remember, radiation is actually the special one. So radiation allows things to be heated without using matter. So radiation does not need particles, it does not need objects to be touching, it does not need objects to be swirling around. Instead, it can actually heat things up without touching. So this is why, for example, a fire can heat you up without you touching it, and why the sun can heat us up without there actually being any particles in outer space with which it has to move, right? It can move through the vacuum of outer space because it doesn't need particles. Okay, so taking a look here, conduction, convection, radiation, you should be able to match these up. All right, so the example in the scenario, so the person can feel the heat of the flame without touching the flame, the soup itself begins to bubble, a person grabs the metal handle and gets burned, and then the actual types of motion, right? So heat motion when objects are in contact and particles are colliding, heat motion when hot fluids rise and cool fluids sink, causing currents, and then the heat motion that can occur without matter, without particles, without anything to make it move. Okay? Question number 14 is talking about work and power. So we have two equations here, the work equation and the power equation. And then also this really important question of would a slower motor have more or less power? Now, remember, you're answering three things, so you should actually have 3 checks marked. All right, so you should actually mark off 3 of these answers. So 1 for work, 1 for power, and 1 for the slower motor. So let's go ahead and talk about those. So remember, work equals force times distance. So work we measure in joules, force we measure in newtons, and distance we measure in meters. So power, on the other hand, is actually the rate at which work is done. So power equals work divided by time, and the units for power is watts. Okay. Now, the important thing to understand is that everybody could do the same amount of work, which is just the force and the distance. So using the same force to lift an object the same distance, the work would stay the same. The thing with power, though, is that power actually makes it faster. So when we have things that are happening faster, that actually means that it has more power. So faster means more power. So let's go ahead and take a look at this. So first we need to calculate work. Stop, please. So we need to first calculate work, and work is calculated by multiplying force times distance. So take a look here. We've got 15 newtons. Remember, newtons is a measure of force. And we've got 3 meters. Remember, meters is a measure of distance. So you should be able to plug these in and calculate work, right? So plug in force, plug in distance, multiply them together in order to get your work. Again, you should choose one of these 3 options for work. Now, once you've done that, we actually have solved our answer for work. We're going to plug that into our power equation. right here. And we need to divide that by the time it took for the motor to work. So in this case, our time, remember seconds tells us time. So we would plug in, sorry. It's hard to write with my mouse. So we would plug in 9 seconds for our time right here, right? So that gets plugged in right here. So the work that you got from the first part divided by the time, which is 9 seconds, that should give us our power. So then you're going to answer one of these, choose one of the correct powers. Okay, and then lastly, we need to figure out, would a slower motor have more or less power? Think about a slower motor takes more time to do things, and remember, it's that means that it's actually not going to have as much power, right? If power speeds things up, so faster means more power, then think about what slower means. Okay, and so that'll be your last question right here. So choose one of these. Okay. All right. Our next question is talking about waves, the terms of waves and their definitions. Okay, so remember, a mechanical wave is any wave that requires matter in order to travel. So this is things like sound waves, for example. They require air in order to travel. But remember, the matter itself stays in place. It just wiggles back and forth in different ways. So the first way is a transverse wave. The particles move up and down perpendicular. Right, so the energy is going to the right here, but the particles are actually moving up and down, so that's perpendicular. Right, so energy to the right, particles up and down, that's perpendicular. They cross over each other. Longitudinal means particles move parallel to the energy of the waves. So in this case, the energy is going to the right. The particles are just moving left and right, so they're not crossing over. That's parallel. That's something, again, like a sound wave where particles just push each other back and forth. Air particles push each other back and forth to transmit sound. And surface particles are combining both of these motions into circles. So you can actually see how they're kind of a circular motion here. Okay, so that being said, when we're talking about waves, remember that the highest point on a wave is called a crest. So it's just a single point, and the lowest point is called a trough. Again, just a single point right here. The amplitude, on the other hand, is the actual height. So that's the total height from the equilibrium up to the highest point. So the height of the hill here. It could also be the depth of the valley. And a wavelength is the length of one complete wave cycle. Again, anytime you see the word length and the word wave, you know that that means wave length. Period and frequency are related to each other. Remember, period is the time for one cycle, and frequency is the cycles in 1 second. They are not the same thing, though. So again, period is like a period of time, the total time it takes for one cycle to happen, which is right here. Whereas frequency is the actual total number of cycles in 1 second, which you can see there's a lot more in this 1 second. All right, so at this point, you should be able to match up the correct answers for number 15. All right, question number 16 is asking about which of the following statements are true or correct about sound waves, so that they can travel through the vacuum of outer space, are longitudinal, are transverse, are mechanical, are electromagnetic, do not require a medium, do require a medium, are faster in gases, or are faster in solids. So let's go ahead and talk about sound waves. So remember, sound waves are mechanical waves. All right, so they are considered mechanical because they do require a medium, right? They need a gas, a liquid, or a solid in order to travel. So for example, sound is a mechanical wave because air particles are needed, right? One air particle hits the next air particle, which hits the next one until it gets all the way to our ear. Specifically, this type of mechanical wave is longitudinal because the particles are moving parallel. So the energy is going from the speaker to the ear, and these particles are actually vibrating back and forth parallel to that energy. So these are actually moving in a longitudinal motion. Now keep in mind, sound is not electromagnetic because it cannot travel in space and it cannot travel in a vacuum where there is no medium. So for example, sound in outer space does not happen because there's nothing to carry that sound in outer space. So it's not electromagnetic, cannot travel in space, and is unable to travel in a vacuum, and is unable to travel without a medium. So it is mechanical, does need a medium, it is longitudinal. So again, taking a look here, you can actually see that longitudinal motion, right? These particles are moving back and forth parallel, going from the speaker to the ear. Now, the speed of sound does depend on the medium. Remember that sound travels faster when molecules are actually closer together, which means that sound actually travels the fastest in solids, because solids are where particles are actually the closest. So, for example, if you take a look down here at lead, glass, and steel, these are all examples of solids. These are much, much faster than the speed of sound in air. The speed of sound in air is only about 330-ish, 340-ish meters per second, whereas in steel, it's actually 5,960 meters per second. So sound travels faster in liquids like water, which is why animals can communicate longer distances in the ocean than we can on Earth. In the air. And it's even faster in solids, right? It's 20 times faster through steel than through air. All right, so this point you should know all of these, so be able to talk about what type of wave it is, if it's mechanical, electromagnetic, does it require a medium, does it not, is it faster in gases or solids, and can it travel in the vacuum of outer space? Again, you're looking for true statements, so find all of the true statements. I believe you should end up with 1, 2, 3, 4 true statements, I believe. All right, the next one is talking about the types of electromagnetic rays. Waves. So let's take a look at these. We talked about how radio waves are used for broadcasting, radio, and TV. Microwaves are used for cooking, for telephones, etc. Infrared is the type of electromagnetic radiation that causes heat, like heat from the sun, heat from fires. Visible light allows things to be seen, specifically allows us to see all the different colors of the rainbow. Ultraviolet light is absorbed by the skin, which over many years can cause skin cancer, which is why we use sunscreen. X-rays can be used to view inside of bodies because they can actually penetrate through your skin, unlike penetrate through your skin and muscle, unlike ultraviolet. X-rays are stronger. And gamma rays are the absolute strongest, right? They come from things like nuclear fallout, but they can actually also be used for good, for example, by killing cancer cells. Now, keep in mind that the shorter the wave is, the more dangerous it is, right? Because it has more energy, more power, and more radiation. So that's why all of these on the right are actually really dangerous, and gamma rays are the most dangerous, right? Ultraviolet can just kind of penetrate your skin and might cause cancer in 60 or so years. X-rays are a little bit more dangerous. That's why we wear lead jackets when we get X-rays, so that we don't get too much radiation. And gamma rays, again, think about nuclear fallout. These are extremely dangerous because they are highly energetic. All right, so at this point, you should be able to match all of these up: visible, infrared, gamma rays, and X-rays. You won't use all of the definitions, so just make sure you're finding the correct definitions for number 17. Number 18, we're talking about which of the following types of shirts will keep you cooler on a sunny day and why. So red, black, or white, those are the 3 color options. So you're going to choose one of these 3 colors, red, black, or white. And then the reason why, you have 4 options for the reason why. So let's go ahead and talk about that here. Sorry, one moment. Here we go. All right, so remember that when light encounters matter, 4 things can happen. First, light can be transmitted, which means it goes through matter without changing. It can just go straight through. This is called direct transmission. So for example, you can see through air. Absorption, this means that light actually gets absorbed and converted into heat, right? So when something absorbs it, it gets warmer. That's why air warms up as it absorbs light. Reflection means light can actually bounce off of a matter surface. So for example, air reflects light off of the Earth, which is why you can actually see the Earth from outer space. The Earth itself is not glowing. Instead, it's reflecting back light from the sun. And then refraction is how light rays can bend as they pass through matter, which is why the sky is the color that it is, because as light comes in, blue light actually gets bent more and bounces around our atmosphere, making the atmosphere look blue. All right, so when we talk about this, transmission means it goes through, absorption means it gets absorbed and turned into heat, reflection means it bounces off, and refraction means it bends. So when we're talking about different colors, right, white objects are actually going to reflect more light. So we have reflection where white light bounces off, and that is why they appear white, because if all of the colors bounce off, we see all of the colors, and so it appears white, as well as it helps to keep you cooler because it's not absorbing any of those light rays. Dark colors like black, on the other hand, are going to absorb all of the light, which is why they appear black, because it's now the absence of light. There's no light to reflect back into your eyes. And so these actually heat up because if they're absorbing all the light, they are actually creating heat. And then other objects, remember that whatever color bounces off, that's the color that you see. So it's going to absorb some colors, but if it reflects red light, then that's why this appears red. But it does absorb the rest of the colors. All right, so at this point, you should be able to figure out which t-shirt will keep you the coolest, right, based on what we just talked about on this slide. But you should also be able to explain why. Is it transmitting, bending, absorbing, or reflecting all of the colors of light to keep you cool? All right, question number 19 is talking about filtering. So it's talking about what color would the following object appear. So we can see a bunch of different colors of light, and one of them is moving through it. And we want to know what color will this object appear. So taking a look at this, again, remember that when light hits objects, it can do different things, right? Transmission means it goes through without changing. Absorption means it gets absorbed, turned into heat. Reflection means it bounces off. Now here's the thing. When we have an object that can transmit a color, the color that gets through is actually the color that you see. And this is what is called filtering. So some objects filter light, like gems, because some light gets absorbed, but the other light gets transmitted. So when we've been talking about, for example, colors that you see on opaque objects, the color you see is the color that bounces off. But when we're talking about the type of object that we see in this problem, it's because some light is actually getting through. So whatever light actually gets through is the light that your eye actually sees. So this is the light that your eye actually sees. And you can see this here, right? We have a object that filters here. And it's filtering out all of the colors. It's absorbing all of the colors except for red, allowing red to get through, which is why this object appears red. It's the same thing why ice looks blue, because it filters out all the colors except for blue. Okay, so take a look again at what color is getting through, and that should help you figure out what color does this object appear. The very last question that we need to talk about is talking about circuits. So take a look at this picture here. It says, what's true about the circuit of holiday lights if one light bulb gets broken? All right, so we're going to go ahead and take a look at what happens if just one of these light bulbs gets broken. So first off, we need to talk about the difference between series circuits and parallel circuits. So remember, series circuit means that there's only one path. So in order to get from the power back to the power, you have to go through both bulbs, for example, or all of the bulbs. So for example, this means that if one bulb actually breaks, then the entire circuit is broken. It's like literally there's now a break here, and so it will no longer work, and so the other light bulb also goes out. Right? So again, if we break one light in series, then the other one actually also goes out because the electrical flow stops. A parallel circuit, on the other hand, actually has more than one path. It has multiple pathways. So even if one light gets broken, it actually still means that the other light stays on, right? So take a look here. If electricity can go through path 1 here, or it can actually also go through path 2 right here. So even if this light bulb on top gets broken, light can still reach the bottom bulb, and so it stays on. Or if the bottom bulb gets broken, light can still reach the top one, and so the top one stays on. Okay. Now, that being said, if you take a look at this picture actually has light bulbs that are both in parallel and series. So you can see 4 different pathways in parallel, right? So this right here is a parallel pathway. Here's a parallel. Oops. Yep. Here's another parallel. And here's the final one. So there are 4 different parallel pathways here. But in their actual rows, they are actually in series with each other. So if, for example, you were to take out one of these lights, let me get a different color here that shows up. So if, for example, you were to break one of these lights right here, what would end up happening is that this actually breaks this pathway right here. So this pathway right here is a single pathway. So this one is actually in series in this row. So just this row is in series. And so all of these light bulbs in this row would actually go out because they're all in series. However, the rest of them would actually stay on because the rest of them are in parallel, right? So you can see here that the rest of these pathways still exist and are not broken. And so these ones are still in parallel. So these ones are still in parallel. And so these ones actually stay on. So in this case, the only ones that go out are the ones that are in series in the same row as the light bulb that goes out. So the only ones that go out are the ones that are actually in series with that same light bulb in the same row. All right, so that should help you figure this out right here. Again, you are going to actually have two answers, so you should figure out what happens to all of the other lights. What happens to the different lights, sorry. And then what happens, and then what kind of circuit is this? Is that should help us figure out number 20. All right, so at this point we are done with our exam. Make sure you get it submitted. Zeros will be entered at 4 p.m. Thanks so much, everyone, and I will see you later.